Thank you, thank you. Gonna talk about how video games, they help revolutionize AI. So today I'm not really gonna talk much about AI in video games, but I'm really gonna focus on how we use this to advance AI. Unity, I'm going to get back to Unity in a moment, is a gaming platform company, but my background is way outside gaming. I was head of machine learning at Uber, general manager for machine learning at Amazon, where I launched the first AI service on Amazon Web Services. I did it at Microsoft, I did it at IBM. So that's my background. Yeah. Very quickly about Unity. We are the #1 choice of gaming platform. We got about 60% of all games developed on our platform. We're on 4 billion devices, 1.9 billion monthly active players. Yeah, so when you kind of think about it, we are just like Uber, Amazon, and Microsoft just in gaming. Yeah. So let's get into artificial intelligence. There's a lot of attempts to claim that Siri and Alexa is AI. It's not. Amazon and Netflix recommendations, it's not. All of these things here are really just smart algorithms developed by even smarter people. Yeah? So they thought it all out. Yeah? There are thousands of people working on Alexa trying to figure everything out. Yeah? That's not AI. Yeah? This is not AI either. And this is not at all AI, yeah? So what is real intelligence, yeah? It's something about acquiring skills and be able to do something with it. It's all very abstract. But the only intelligence we really know is the one in biological systems. So that's where we're going to start out, yeah? It's really 5 principles that drives the need for intelligence in nature, yeah? So rather than trying to explain what it is, I'm going to give 5 principles that drives intelligence. It's the need to consume energy to survive, to fight entropy. It's the avoidance of getting eaten when you try to get energy yourself. It's multiplying, procreation, and it's being aware of physics. You have to really watch out for physics because you can fall down and kill yourself while trying to get food. And finally, it's agency. It's about shaping the environment around you to improve survivability. Yeah. Nature invented this kind of stuff here. Yeah? That's what nature invented to get through these 5 principles. Yeah? So it created infrastructure. Yeah? Things like chemical mechanisms, cellular structures, multicellular organisms with messaging, neuromuscular junctions, and sensors. Lots of sensors, yeah? So this is all the stuff that nature created to do intelligence, yeah? So if you think about it, what's a game engine? Yeah? A game engine is a real-time spatial thing that has a physics engine in it, yeah? So in fact, if you think about it, your popular game engine that you develop all these games on is really your private AI biodome, yeah? This is how you can actually explore the boundaries of AI in a very similar way to as nature did it, yeah? And if you look at our ecosystem, well, we have tons and tons of games, yeah? Games that have, difficulties in them, games that have holes in the ground you can fall in and kill yourself, high fidelity graphics, etc., etc. Yeah. One of our closest partners is DeepMind. Some of you probably heard about DeepMind, the guys that beat the world champ in Go. They're using Unity, and they're one of these few companies out there that really understand that by using a gaming platform, you can put your AI development on steroids. Yeah. When we talk about AI in gaming, we really talk about using nature's method of learning, which is observing, taking action, and then reap the rewards or the penalties or punishment from those actions. Yeah? And essentially learn. Move from exploration to exploitation, yeah? This is also what Amazon is doing every time you shop on their website, yeah? By the way. I'm going to show you how capable reinforcement learning is in an example here. Yeah? We start from Tabula Rasa. Everything I show you today is from scratch. So there's no cheating. It learns from scratch. It's only given limited information. In this case, observe the pixels. You have 4 actions, and you have 2 rewards. 1 negative for being hit by a car, and 1 positive for gift pickup. Yeah? We want the yellow chicken to figure out if it can learn to cross the road, picking up gift packages while avoiding getting hit by a car. Yeah? And it looks like this initially, first few seconds. You can see that it really knows nothing. Yeah? It's moving more backwards than forwards. It's completely random. But in a moment, it will capture 2 bits of information. First, it will pick up the gift package and then get killed. Yeah? But let it do that for an hour, and this is what it looks like. Yeah? It gets pretty good. Coming from scratch, knowing nothing, it can do this. Yeah? It gets really good at picking up packages. It avoids cars some of the time. But let's see, if we give it a little more training in a moment here, 5 additional hours of training, you have a superhuman chicken crossing the road, picking up packages, avoiding cars. And remember, these cars are coming in completely randomly, and so are the packages. Yeah? So it has never seen this particular scenario before. Yet, it's unstoppable and will never get killed. Yeah? From scratch. Yeah? Let me show other examples. This guy here, 4 legs, 2 joints on each leg. Could you imagine writing in some language how to move those legs to move forward? No. Just like the chicken, these guys are allowed to wiggle around for an hour and they will figure it out. They will figure out how to move forward. Yeah? Same with these guys. Anyone with small children, 9, 10-month-old, please, can you stand up now? And they can't. It's hard. You need to control a lot of things, yeah? The same algorithms as with the children, with the chicken, can teach these guys to stand up or these guys to walk, yeah? So you have to understand this is Tabula Rasa, yeah? I did not cheat. I did not code in there. You have to move the legs like this, yeah? I just said here's the geometry. You get a rewards function, a positive reward moving forward. And it looks something like this. So I can see we are walking sort of the same way that the computer figures out is the best way. I can restart this 1,000 times. It will always end up walking something like this. Yeah? There are other things in there. Yeah? Like in this example, from scratch, what we really do here is that we actually tell, no, I'm going to let you in on this. Yeah? When the agent, the blue agent, exits the room, if that first big cube is orange, it has to use the orange door, or otherwise, if it's red, it has to use the red door for exit, yeah? But I don't really tell it that. I just tell it right or wrong as it tries, yeah? And looks, after a short while, it knows that if the block is orange, I use the orange exit. If it's red, I use the red exit, yeah? Why is this interesting? Because I never told it that color matters, yeah? It figures out, it learns what matters, yeah? Not size, not location, but color. Color is the thing that makes me succeed in this case, yeah? So it's sort of a glimpse into a world where we don't program the computer, but the computer is just given some success criteria, and then we go from there, yeah? Another example here, you saw the spider moving around. In this example, we actually add another machine learning model to it. The model that says, go left, left, right, it navigates, yeah? But it does not worry about how to move the legs. The legs, that's a different story, yeah? Can you imagine when we stack machine learning models like that, where they each have their piece to take care of, but when you stack them, they work as a wholeness, yeah? I have other examples. These 2 guys learn to play. Yeah? I just told them, don't drop the ball, so they will play each other, yeah, endlessly. Or soccer. I saw the women's semifinal last night. It went well for some. One player, offensive, which means I reward you for scoring. The other one, I reward you for keeping the goal clean. Yeah? And how do I train them? I just put them together. Yeah? They play each other. The defensive player gets better and better. The offensive player, the striker, gets better and better until they can't get any better. Then I just copy them so that I have two teams that play each other. What's interesting here is that the defensive player apparently becomes a goalie. Apparently this is actually a really, I didn't tell them to do this. They figured out that standing in front of the goal is a good idea. And the offensive players, they move along the line. They actually run sideways if you look at it, because the little white thing is an eye, and that's how they look, and they can see the field that way. Yeah. I want to show you another example. In this example, whenever you hit the ball, you freeze up for 2 seconds. Yeah. So hitting the ball, it has a penalty associated with it. So you have to be careful hitting the ball, unless you can actually get something out of it. Yeah. And I'm going to show you an individual rewards example. These guys, they get an individual reward for scoring. But since there's this risk that trying to score, someone else may grab the ball and score instead, they end up never agreeing to actually score, if you notice. They're just fiddling around, yeah? One example of a bad reward, yeah? If you have a team, don't give them individual rewards because they're not going to work together, yeah? Let me show you another example where we put the field up in the air, yeah? And this poor agent is trying to solve this problem all alone, yeah? But because it freezes to ice all the time, it can't really get the ball up, yeah? So we put 3 in there, and look what happened. We give them a collective reward which says when you score together, you get rewarded. I did not tell them how to work this out, yeah? So here you have 3 individual systems very quickly learning how to play together to achieve a common goal, yeah? Which brings me on to some very, very interesting and very recent breakthroughs, which is around intrinsic and extrinsic rewards. Extrinsic rewards are the ones I've shown you all the time. Is achieving something like getting a score, getting rich, yeah, collecting something, getting points, yeah. Intrinsic rewards are more complicated. They're examples like curiosity, happiness, love, empathy. They're stuff we have in us that nature gave us because it helps survivability. But it's not something that sits in a bank account, yeah? It's in here, yeah? It's about getting happy. And what does this have to do with computer science and AI? Well, everything, yeah? Because it has a purpose. It's a trait. Reinforcement learning, as I have shown you today, has some limitations to it. Some stuff is just too hard to learn randomly, yeah? And I will show you an example of something. There's a long chain of very, very impossible things that you have to just know to get to the reward, yeah? And you can't solve it randomly. You can't just randomly dabble around and figure it all out, yeah? You have to have agency. You have to have some trait in you to solve this problem, yeah? So what we did is that we picked curiosity, yeah? We took one trait. Scientists are curious, squirrels are curious when they look for food, etc. Yeah? Curiosity is very, very fundamental nature. And we put it in math, and we found the important point, which is the minus log. I'm not going to go into that. It's not as hard as it looks, actually. It just means that instead of trying to be perfect, you're trying to figure out what you don't, to figure out what you don't know. Yeah? And what you don't know, you go and explore first. So look at this example. The agent is in a house with rooms. It needs to find the push button and push the button, etc. It needs to learn all that. But clearly, by just moving randomly, sort of left and right and forward and backward, it's not really going to figure out much. You can keep doing this for hours or days or years, and you probably won't learn it ever. Yeah? Let me show you an agent that favors curiosity, but no extrinsic reward. It doesn't get rich here. It's just purely, deeply curious. And it looks like this. It goes from room to room. It sees these pyramids of stones, and it touches one of them and figure out if I touch them hard, something happens. So let me explore this a little more. Look. This is not me. This is the computer, yeah? Figures out that, if I move fast into it, something happens, yeah? Combine it with curiosity with an extrinsic reward, and it figures out that I push this button, I find this pyramid somewhere, go, yeah, there it is, and the extrinsic reward is the gold bar, the cube. Yeah, collect the cube, come on, go, there it is. Yeah. So it can suddenly solve an impossible chain of tasks that it never knew about because it's curious. Yeah. If I put a TV set in front of that agent, the curious agent, it gets stuck, by the way. And it will stand there all day, 24 hours a day, watch the TV because it's always something new going on. Yeah? It's an example that curiosity is not going to solve all problems. There's going to be something else, like getting hungry to get away from the TV, yeah? Something like that. Yeah? So we call that the TV trap. And it's real. It's actually real. If we put a TV into this, it will get stuck in front of the TV. You also call it the Netflix trap. Let me quickly show you Popo. Popo is a virtual robot. It's the dog. Just with all the other examples, it knows nothing, yeah? And what I'm doing is that I'm basically training it. It will learn everything from moving the legs to picking up the stick and give it back to me. And when I bring this to life, it looks like this. This is not a Disney animation, yeah? There's no animator here. This is all physics and 3D moving, using reinforcement learning, and the reward is bringing back the stick to me, yeah? I throw the stick with the mouse, and whoops, there we fell over. I want to tell you one thing. One day I was going to show someone that I could get the dog to fall over by moving the stick left and right rapidly. And I did like this, move the stick left and right. You know what it did? It grabbed the stick from my hand or mouse, if you want, turned around and dropped it, which is kind of something I experienced before. Yeah. We did a toolkit. It's all on GitHub. It's all open source, where we made it available to the rest of the world. To everything I showed you here, you can actually go and download, and there's all the code there, and people can experiment with it, and we have thousands and thousands of students and researchers using this now to push the boundaries of AI. Yeah? I want to get quickly back and say that we have been cheating a lot because we have been looking at nature and stealing from nature, stealing ideas from nature, because nature has been through all this already. Yeah? So I have a long, long list of very interesting things. There's some stuff we already did, there's stuff we haven't done yet, and then there's probably stuff we're not aware of yet. Yeah? But I do want to say one thing, which is, let's take a look at culture too. And human culture has evolved in its own way over about 200,000 to 300,000 years, Homo sapiens. 100,000 years ago, tried to migrate, it failed, and then tried another time a little later. This time made it all the way to Australia, and were very successful. Well, we're all here today, yeah. Something happened in that period. Something happened, this Löwenmensch, this figure is 32,000 years old, so someone 32,000 years ago were crazy enough to put a lion's head on a human body, yeah? Which tells us that someone started to get crazy ideas, imagine stuff, yeah? And that is important, because remember, there's no Moore's law. You know Moore's law is the one that computer chips are twice as fast every 18 months, yeah? Did not happen for the brain, yeah? Our brain is the same today as 70,000 years ago. You check the DNA, it's the same processor. So what changed? What made it possible to move from picking berries in the forest to put a person on the moon? Emergence, language, collaboration, and anticipation of other people, working together more and more efficiently. That's the difference, yeah? So can you imagine when these AI systems, they start figuring out how to work together without our help? I want to leave it there. Thank you very much.
We're going to take one question from the audience via Slido, and the question is there a significant difference in the quality of learning depending on whether you use positive or negative reinforcement?
No. There's no difference in that. No, I can't think of any. It's really just whether it adds up or subtracts.
And is that the same with humans, do you think?
Whoa, that's a loaded question. I do think that we feel it's tricky, yeah, because I think that it doesn't really matter whether we guess that, hey, that was good or that was bad. However, there's a lot of other traits in us that we like to hear more, this is good, and that encourage us to explore more, rather than, no, don't do that. That does not really encourage you to explore more, yeah. So it's very, very complex. Machine learning is not at that stage, but it is getting there, step by step.
Beautiful. Thank you, Danny.
Okay, thank you very much.